Okay, thanks a lot for the introduction. And it's a pleasure to be here online, and thanks a lot to the organizers for giving me this chance to speak here. I wish I could have been there in person. Anyway, so about this talk is going to be about some framework of combination theorems in conformal dynamics, and I'm not exactly using the word complex dynamics because, as the title suggests, there's going to be some interbreeding involved here. We are not just going to work with rational maps or polynomials. There will be combinations of species of different genre, something of that sort. And one advantage of speaking on the last day of a conference is that most of the notions are stuff that I'm going to talk about, at least have been defined in one way or the other in the previous talks. Okay, so let me get on with it. So I apologize. So this slide, I just realized this morning, has a thematic similarity with the second slide of Misha Rushchanka. But so I'm trying to sort of get across the same message here, that there are bridges between rational dynamics and all these different themes that are near and far, rather, that I'm going to sort of push in this talk. So what are the main things? The main player in the talk is going to be some combination theorem of polynomials and some class of groups. And the groups that will play a key role in this combination theorem setup are reflection groups or Kleinian reflection groups. There is also a holomorphic analog of this combination theorem that I'm going to state later, but today for this talk, I'm only going to restrict to the antiholomorphic setup, so antiholomorphic maps and reflection groups. And along the way, the tools that we will develop will have applications to various topics in complex analysis, such as welding and conformal removability and so on. There's also applications of this line of ideas to correspondences, both holomorphic and antiholomorphic, but today I'm not going to touch that topic at all. And there are also links with some group theoretic questions like groups of quasi-symmetries of certain fractals. And probably the only farthest topic from rational dynamics is that of orbit equivalence. That's a notion that appears in group theory. If time permits, I'll say something about some applications of our combination theorem framework to questions in orbit equivalence. Right, so to talk about combination theorems, one must first name some of the early contributions and the recent works in framework of combination theorems in groups, geometry, and dynamics. So the first thing that comes to one's mind is the Klein-Musket combination theorem, which combines two Kleinian groups. And although today's talk will have almost nothing to do with this combination theorem, on the other hand, the Bayes simultaneous uniformization theorem that allows one to make two Fuchsian groups to produce a single quasi-Fuchsian group, which shows that the space of all quasi-Fuchsian groups viewed as representations is the product of two copies of the Teichmüller space, is going to, many of our results are going to be inspired by this setup of combination theorems. There is also the Thurston's double limit theorem, which I'm going to state here. I'm not going to state it, but I have written it in a language that's convenient for me. You take two projective measured laminations on the Bayes boundary, for instance, or you can think of them as two groups, two projective measured laminations or two groups on the Bayes boundary of a Teichmüller space, and you want to combine them together to get some kind of a Kleinian group. And on a related note, there's the Duodey-Hubbard mating theory for polynomials, where you take two polynomials and glue them, if you can, to get a rational map acting on the Riemann sphere. So these ideas are going to play, they're going to recur in my talk. However, I'm not going to be working with two groups or two polynomials. Rather, I'm going to be working with combination. I'm going to give combination theorems for polynomials with suitable collections of groups. And this flavor of combination theorem, where you try to make two different objects of conformal dynamics, first appeared in the work of Willett and Penrose, where they managed to construct matings of quadratic maps, rather quadratic polynomials here, and then quadratic rational maps with the modular group in the more recent work of Willett and Sean Willett and Luna Lomonaco as algebraic correspondences. Now, the starting point of our work, as I'm going to start in the next slide, is to try to come up with some kind of a general framework of these matings of polynomials with not just the modular group, or in our case, some general class of reflection groups, but not as correspondences, but as a single partially defined map on the Riemann sphere. Okay, so how does the story start? The story basically involves this class of maps called Schwarz reflection maps. So what are Schwarz reflection maps? Let me start with examples, because essentially the way the theory started, it was Nick Makarov and Sin-Yop Lee who were playing with these Schwarz reflection maps because of their connections with complex analysis and statistical physics. And in the process of their experimentation, they saw some very interesting pictures which suggested that there's some kind of combination theorem going on in the background. So I'll come to that in the next slide. Just to keep things easy, I'll not give too many definitions, but I can't avoid the definition of what a Schwarz reflection map is. So a domain, omega, in the complex plane, this is, or in the Riemann sphere, is called a quadrature domain if it has the following property. Namely, you have an antimeromorphic function, sigma, from the closure of the domain to the Riemann sphere that fixes the boundary pointwise. So how should you be thinking of a quadrature domain? Just think of it as a domain, not necessarily simply connected, although simply connected quadrature domains are going to be the only things I'll talk about today. But just take any domain with piecewise real analytic boundary with, say, finitely many singular points. And since the boundary is piecewise real analytic, every point is going to have a small neighborhood where you have an honest Schwarz reflection function, where inside flips out to outside, outside goes back to inside, so it's a degree 2 antiholomorphic map, and the curve is pointwise fixed. Now, if you have a domain with such a boundary, you have the Schwarz reflection map piecewise defined on the boundary. There is obviously no guarantee that these maps will extend analytically to the whole domain. And even if something extends, it doesn't have to be a well-defined continuation. Quadrature domains are precisely those kind of domains for which the boundary Schwarz reflection maps extend antimeromorphically to the domain, to the whole domain. Particularly of particular importance, at least for today's talk, are simply connected quadrature domains. And it's not a hard thing to show that a simply connected domain in the Riemann sphere is a quadrature domain if and only if the Riemann uniformization map from the disk to the quadrature domain extends as a rational map of the whole Riemann sphere. So here is, a trivial example of a quadrature, a simply connected quadrature domain is a round disk. It has this Mobius anti-reflection map. A non-trivial example is given by such a map. So what is this? This is just a rational map that is univalent outside the unit disk. And the image of the exterior of the unit disk under this map is the complement of the so-called deltoid curve. So this is your omega. And what is your Schwarz reflection map in this situation? You just define your Schwarz reflection map as the branch of F inverse that takes you from takes the domain to the complement of the disk. Then you apply 1 over z bar that takes the complement of the unit disk to the interior of the unit disk. And then you go back again by F. So the standard reflection map 1 over z bar over here is semi-conjugated to the Schwarz reflection map of this quadrature domain. And that's how all Schwarz reflection maps of simply connected quadrature domains appear. So this gives a very general recipe of constructing Schwarz reflection maps for simply connected quadrature domain. Now, this particular example was probably the first non-trivial example that was studied by Makarov and Lee. So what happens dynamically? Dynamically, the Schwarz reflection map is only defined outside the deltoid. So it's a partially defined map. And for a partially defined map, two important things come up. Two important dynamically meaningful sets come up, namely the escaping set. So that's the set of all points that will eventually escape to this region where the dynamics is not defined, and the non-escaping set. So the set of all points where the Schwarz reflection map can be forever iterated. And if you try to draw the dynamical plane, the escaping set and the non-escaping set, this is what it looks like. So the escaping set is the interior of this cauliflower-ish curve. every point here eventually escapes to the brown region where the map is not defined. On the other hand, outside of this green curve, the dynamics is forever defined, and just the concrete definition of the Schwarz deflection map allows one to check that, if you believe this picture at least, that this is the non-escaping set is a Jordan disk, closed Jordan disk, and the dynamics over there is conformally conjugate to z bar squared. What's happening inside is not so clear. I mean, point-wise, it's clear. Every point is eventually escaping there. But the tessellation picture that you get by pulling back the fundamental tile, so you get this rank 1 tiles and then rank 2 tiles and so on, this picture looks, up to a conformal change of coordinate, exactly the tessellation of the unit disk given by the ideal triangle group. So in this sense, you see features of reflection groups as well as polynomial dynamics in the same dynamical plane here. There are more general examples of this sort. So here's another example that gives rise to the same kind of matings where you have, now instead of the map z bar squared, if you take the basilica map z bar square minus 1 and the same ideal triangle group, there is a certain Schwarz reflection map that gives rise to the mating of these two guys. So what is this thing? You take the principal cardioid of the Mandelbrot set. So we all know that the principal cardioid of the Mandelbrot set has a Riemann map, which is a polynomial. Therefore, by this fact, the principal cardioid of the Mandelbrot set is a quadrature domain. But the Schwarz reflection map of the domain itself is not so interesting. So instead, you define this partial dynamical system. You take as your face plane the principal cardioid of the Mandelbrot set and a disk and a circumcircle, this blue guy. Inside, you define the Schwarz reflection map of this quadrature domain, and outside, you just take reflection in this circle, in the blue circle. And if this is, so this is what my omega A is, so the only choice of the parameter here is the center of this blue disk. Depending on the center of the blue disk, you have a one-parameter family of Schwarz reflection maps here. And these Schwarz reflection maps, because they are only defined on the union of the cardioid and the exterior of this blue circle, they also have a non-escaping set and an escaping set. Escaping set is a set of all points that eventually escape here. And that, so the picture obviously cannot show the whole dynamical plane because there is a point at infinity here. I'm only showing the bounded part, the part contained in here in this picture. And for a suitable choice of A, namely if we choose A to be 0, then one sees that the non-escaping set looks very similar to the standard basilica, and the escaping set again looks like the ideal triangle reflection. So that's another visual suggestion that there's some mating framework, mating theorem underlying this picture. Now, going beyond the ideal triangle reflection group, if you look at this particular rational map, so all these formulas don't matter. I'm just trying to show some pictures that will lead us to some general framework of combination theorem. If you look at this particular rational map, it's an extremal rational map in the sense that if you take a cubic rational map, so this rational map is in fact univalent on the complement of the unit disk, and it sends the complement of the unit disk to the complement of this pinched curve, which is essentially like a union of two deltoids. It's extremal in the sense that for all such rational maps of degree 3, this guy has the maximum number of cusps and double points on the boundary. Okay, so again, since this rational map is univalent on a round disk, its image, namely this gray region here, is a quadrature domain. So there is a Schwarz reflection map. And once again, if you try to draw the escaping and the non-escaping set of this particular Schwarz reflection map, this is the picture that you get. The dynamics on the non-escaping set is in fact conformally conjugate to the simple map z bar to the 3 in this case. And the picture that you see on the escaping set looks like the limit set, or at least the filled limit set of this particular reflection group. So just compare this picture here, the escaping set, and this picture over here. So once again, you see a similar mating behavior. Okay, now the question is, how can we formalize this thing? If I take a map of this sort, I can see that the dynamics outside is that of a polynomial up to a conformal change of coordinates. But what is really the dynamics inside here, and or maybe in this case here? To make sense of, in order to get a conformal model of the dynamics of the Schwarz deflection map on the escaping set, we need to define what we call the Nielsen map, because Nielsen actually introduced these maps in his work on surface automorphisms. These things he called Nielsen developments. So the simplest Nielsen map in the case of the ideal triangle group is given as follows. You have a fundamental domain of the ideal triangle group. The reflections in the three sides of the fundamental domain are, let's say, row 1, row 2, and row 3. And you define your Nielsen map over here as reflection with respect to this circle, and in this region as reflection with respect to this blue circle, and in this region as reflection with respect to this green circle. If this is your Nielsen map, then we proved with Singyop-Lee, Michalevich, and Makarov that the picture, as you see here, is an honest mating of the map C bar squared and the Nielsen map of the ideal triangle group. So, and I'm not going to give you an exact definition of what I mean by conformal mating, but the definition of conformal mating that we use here is exactly the same as the definition of conformal mating of two polynomials. You take two copies, like how Pascal was describing earlier today. You take the lower hemisphere and the upper hemisphere. So you think of this guy as a lower hemisphere, or maybe upper, and this guy as the lower hemisphere. You observe that the Nielsen map restricted to the circle is actually an orientation reversing map of degree 2. So there is a topological conjugacy between these two boundary actions, and you glue these two spheres using this conjugacy. Once you do that, you're going to get a topological two-sphere with a topological map defined on the whole sphere minus whatever is represented by this region. So you get a partially defined dynamical system on a topological two-sphere. And then you can put some conformal chart, some conformal coordinate on this topological two-sphere that turns all these maps into antiholomorphic maps. Okay, and similarly, let me just state that in the case of the circle and cardioid family, I've shown you in this picture that the dynamical plane of this particular map corresponding to A equals 0 looks like a combination of the Basilica antiholomorphic polynomial and the ideal triangle group. And this is indeed the case in more generality. So every geometrically finite map, again, geometrically finite essentially means hyperbolic, parabolic, and parabolic maps and Michalevich maps. So every geometrically finite quadratic antiholomorphic polynomial can be mated with the Nielsen map of the ideal triangle reflection groups, and such matings are realized in the circle and cardioid family for various values of A. That's good. That settles the situation, that describes the situation for the ideal triangle group. What about this picture here? How do I describe the dynamics, or how do I describe a conformal model for the dynamics of this Schwarz reflection map on its escaping set? Now, before I do that, I need to figure which class of groups am I working with. The class of reflection groups that are going to appear in this mating framework are the so-called kissing reflection groups. So a kissing reflection group is a very simple-minded object. You take a finite circle packing, which is just a finite collection of finite connected collection of circles with non-empty, with disjoint interior, like this one here, or this one over here. And your kissing reflection group is just the group generated by reflections in there. A specific example of a kissing reflection group is an ideal degon reflection group. Or let's say the regular ideal degon reflection group, where you have your fundamental domain is a regular polygon. So, for instance, gamma 2 would be this guy. this base point is going to be important for us because beyond the ideal triangle case, reflection groups are not rigid, so they do have whole Teichmüller space. And I'm going to think of the regular ideal Degon reflection group as a base point in the Teichmüller space of such groups. And I'm going to work with the closure of the Baire slice of gamma D. So what does that mean? You start with, for instance, if you start with a reflection group generated by these four reflections in these four circles. So your fundamental domain is going to be this guy and the exterior. When you stay in the Baire slice, all you're doing is you are quasi-conformally deforming this fundamental domain, but you are not touching the conformal class of the exterior component of the fundamental domain. So as long as you're in the Baire slice, all of this can be stated in terms of the index 2 subgroups of these reflection groups. And that would justify the use of the terminology Baire slice. But let me refrain from doing that. So you just quasi-conformally deform the base reflection group gamma D such that the dilatations are supported in the unit disk. So this is the limit set of the regular Degon reflection group. And you're going to quasi-conformally deform the interior, essentially quasi-conformally deform the fundamental domain, but don't touch the outside at all. And then you go to infinity. You let these things degenerate. And the degeneration in this situation is rather simple. Everything on the boundary is geometrically finite. All that can happen is your circles may touch. This is an example of a point in the boundary of the Baire slice. Or this is an example, more complicated example. So this is the class of groups I'll be mostly working with. And in order to formalize this mating framework, or what am I seeing in this picture, if I want to formalize that, I need to define an analog of Nielsen map for these kind of groups. So in general, for a kissing reflection group, a Nielsen map is a very simple-minded thing. You just take an arbitrary circle packing. Your Nielsen map is just going to be reflection with respect to D1 on D1, or in general, reflection with respect to DI in the circle DI. On the disk DI. So that's your Nielsen map. What is the advantage of this Nielsen map? The main advantage is that the Nielsen map and the group, they have the same grand orbits. And since the group, when you're trying to combine a group with a polynomial, you have this mismatch of a group dynamics on one side and a semi-group dynamics on the other side. As we know from the Bullet-Penrose or Bullet-Lomonaco work, if you really want to glue these things without killing the group behavior at all, what you need to be working with is a correspondence. But in the simplified setup of a map, instead of working with the full group, you make this group and the polynomial meet halfway. So what does that mean? You extract a single map from the group, which is your Nielsen map, but in such a way that you don't lose the dynamics. You don't lose the structure of the orbits. The grand orbits of this map and the group orbits of gamma are exactly the same. So once you have this notion of Nielsen maps for kissing reflection groups, we proved with Kirill and Makarov that this picture is a special case of the following general theorem, namely, you can make the special map Z bar to the D with Nielsen maps of any kissing reflection group in the Baire slice of gamma D plus 1. So I should say, why am I only working with Baire slice closure groups while mating? Well, you don't mate two rational maps, right? You mate two polynomials. And you look at the interesting parts of the dynamics, namely the filled Julia sets. The groups on the closure of the Baire slice play a similar role. They play a role that polynomials play in rational dynamics. If you take a group in the closure of the Baire slice, they all have an invariant component in the domain of discontinuity. This is what you can morally think of as the basin of infinity. And then you have the limit set, and you look at the restriction of the Nielsen map on this filled limit set. This is going to play the role of a filled Julia set. So instead of gluing to filled Julia set, you glue the filled Julia set of a polynomial with the filled Julia set of a group on the closure of the Baire slice. And you can indeed do that if you restrict yourself to this particular map Z bar to the D. You can mate it with any group, the Nielsen map of any group on the closure of the Baire slice of the D+1 gone reflection group. And all such Schwarz reflection maps arise from a very explicit class of univalent maps, which is also called class sigma. Okay, so these are the examples that I wanted to describe first. Okay, any questions so far? All right. So once you have all these examples, you want to have, now you want to build a general theory of these matings. So now essentially, once you have the whole collection of groups on the Baire slice closure of the ideal D+1 reflection group, you don't want to just mate Z bar to the D. You want them to be mated with arbitrary, let's say post-critically finite antiholomorphic polynomials. And there are many problems here. First thing, earlier, we were not looking at topological obstructions at all. We were gluing two disks or a disk with a compact. But now we are going to glue two compact sets, two filled Julia sets, or a filled Julia set and a filled limit set. And of course, then the whole problem of topological obstruction or Moore obstruction will come into play. Let me state the general combination theorem first, and then I'll say what new techniques are required to prove a theorem of this sort. So this is a joint work with Michel Lewitz, Sergei Merenkov, and Dimitrios. So suppose that P is a post-critically finite hyperbolic antipolynomial of degree D, and gamma is an arbitrary kissing reflection group lying on the Baire slice closure of the ideal D+1 gone reflection. Then the best theorem that you can hope to prove is that these two objects are conformally mateable if and only if there is no topological obstruction, as long as you can glue them topologically to get a sphere. And that turns out to be the case. So I should say a word on topological mateability or Moore obstruction of these guys. So in fact, this mating, the definition of this topological mating is exactly how the Doherty-Hubbard mating of two polynomials go. You, instead of now taking two polynomials, you're taking a polynomial restricted to its filled Julia set and a Nielsen map of a reflection group restricted to its filled limit set. But the question is, in the polynomial case, there's an obvious way of gluing them. You identify T with negative T, the point with external address T, with the point with external address negative T. That's obviously because both the polynomial, I mean, when you glue two polynomials, they have the same external class. Now, how are you going to glue the dynamics or the filled Julia set of P with the filled limit set of gamma so that you can, so that the gluing is dynamically meaningful? And the answer really lies in the fact that since you're looking at Baire slice closure groups, what is the external map of this dynamical system? What is the external map of the Nielsen map? So what's happening here is that the dynamics outside is nothing but the Nielsen map of the ideal foregone reflection group. See, outside, this fundamental domain is just an ideal foregone. So if you conformally map the exterior to a disk, what you'll get is simply the Nielsen map of an ideal foregone reflection group in this case, which is an orientation reversing degree -3 covering. And the external class of any cubic antiholomorphic polynomial is Z bar to the third, which is also an orientation reversing degree 3 covering, degree -3 covering. So those two guys, namely the Nielsen map of the ideal foregone reflection group, which is the external class of this Nielsen map, and the external class of a degree 3 polynomial, let's say, are topologically conjugate. And when you glue the filled Julia set of P with the filled limit set of gamma, you glue them according to this, you glue them via this particular topological conjugation. So if this topological conjugation is H, let's say, then you glue the point with external address T with the point with external address H of -T. And then the whole thing makes sense. You may or may not get a topological sphere, but if you get a topological sphere, then you have a partially defined dynamical system on it for free. And it turns out, so obviously one direction here is obvious. The main point is to prove the reverse direction. If the thing is more unobstructed, if you take these two dynamical systems, glue them using the prescription that I just mentioned, and you get a topological two-sphere with a partially defined map on it, the question is whether there is a conformal structure on that sphere that turns everything into an antiholomorphic map. And what kind of antiholomorphic map are you going to get if you manage to do that? So the answer to the second question is easy. It turns out that if the things are matable, then the conformal mating is always going to be a Schwarz reflection map or a piecewise Schwarz reflection map, which means that Schwarz reflection maps, the examples that I showed you in the first few slides, they're not just arbitrary. If a reflection group is matable with an antiholomorphic polynomials, it's always going to lie in the class of Schwarz reflection. Now, the principal difficulty in proving this theorem is that we don't have a Thurston theorem. When you try to mate two polynomials, post-critically finite, let's say, obviously you try to apply Thurston theorem. And the reason you can do that is that the topological mating of two polynomials is going to be a branch covering of the sphere. In our case, P is defined on the whole filled Julia set, but what about the Nielsen map? The Nielsen map is defined on the union of these disks. In particular, it's not defined on the fundamental domain. So the Nielsen map is not defined on the filled limit set. It's only defined partially. So the topological mating of these two guys is not going to be a branched cover. There's no hope of applying Thurston theorem directly in order to get a complex structure or in order to geometrize this topological gadget. Now, to circumvent this difficulty, one needs to use a new connection between antirational maps and Kleinian reflection groups, which I'm going to talk about now. So what's the rough idea? The rough idea is that instead of trying to directly mate these two guys, you try to mate the polynomial P with another polynomial. And now you may ask, but that's not what we wanted to do. We wanted to mate the ideal, the Nielsen map of gamma with P. So why would I try to mate P with some other polynomial? And that's where this particular picture helps you. So what do we see in this picture? Here is the limit set of a reflection group. And here is the limit set or the Julia set of an antiholomorphic polynomial. In fact, critically fixed. There are two, it's a cubic antiholomorphic polynomial, both critical points are fixed. And they are identical topologically. The limit set of this guy and the limits and the Julia set of this guy look homeomorphic. Similarly, in a slightly more general setup, if you look at the standard Apollonian gasket, there's the reflection group generated by these four circles. This is your limit set over here, and this is the Julia set of a critically fixed antirational map of degree 3. Again, the limit set of this and the Julia set of that look indistinguishable from the topological point of view. And here's another picture, but let's just look at these two. So what am I trying to say here? I'm trying to say that instead of mating a polynomial P with this group, we might as well mate the polynomial P with this polynomial first, and that we can do using Thurston theorem if there is no more obstruction. And then we'll try to figure how to go back from this guy to that guy. So that's another thought. That's the step 2 of the. But if I can formalize this observation that given any kissing reflection group, there is a partner, namely there is a critically fixed antiholomorphic rational map such that the Nielsen dynamics here is topologically conjugate to the antirational dynamics on this Julia set, then I have a canonically associated rational map to a reflection group. And then this, in fact, we believe is a new line in the Fatou-Sullivan dictionary because, in fact, Fatou wrote in one of his early papers, one of his papers from 1920s, I think it's something that appeared in some memoir, I forget which one, where he said that the visual similarity between limit sets and Julia sets are too stark to be coincidental, and there should be a synthetic theory of some sort to to combine these things. And well, so the reason I'm saying is that he actually foresaw this thing way before Sullivan entered the picture. Now, of course, we know that there are similarities between these fields, and of course, much has been said about the connection between these two fields in this conference. The thing that I want to say is that in very special cases, in the case of kissing reflection groups, this dictionary or this connection between Julia sets and limit sets is not just visual, it's a precise dynamical link. So let me state the theorem. I should say that this picture is from joint work with Russell Lodge, Michal Lubitsch, and Sergei Merenkov, and with Russell Lodge and Yusheng Liu, we generalized it to the collection of all kissing reflection groups. So it turns out that there is, in fact, a bijective correspondence between kissing reflection groups of a given rank with connected limit sets and critically fixed anti-rational maps. In other words, you give me any kissing reflection group with a connected limit set, say this one, I can find a critically fixed anti-rational map such that the Nielsen dynamics over here is topologically conjugate to the rational dynamics over here. There are many applications of this dictionary, but I'll not get into that. So just a one-word sketch of the proof here. How can I cook up a rational map from a reflection group? So here, the idea of using Nielsen map turns out to be of paramount importance. If you just looked at the group itself, you would never recognize any rational map directly from it. Instead, once you look at the Nielsen map of this reflection group, the Nielsen map is partially defined. However, it's defined on the entire limit set. It's not defined in this region, and somewhere else, or maybe outside here. In any case, let's look at this guy. So your Nielsen map is defined on this disk minus this fundamental domain component. And the restriction of the Nielsen map here is actually the Nielsen map of an ideal triangle. Now what you're going to do is you're going to extend this map to this whole component as z bar squared. So you just topologically replace the dynamics of Nielsen map here by z bar squared, and you do the same thing here and there and the outer unbounded component. Once you do that, you actually have a branched cover, and then you can apply Thurston realization theorem to realize that branch cover as a critically fixed anti-rational map. Then, of course, one needs more work to prove that this is a bijection, but yeah, I'll not talk about that. Okay, so what is the advantage of this dictionary? So the main advantage is that I wanted to mate a polynomial with the Nielsen map of a group lying on the Beer's boundary, and instead of mating the polynomial p with the Nielsen map of the group, I'm going to mate the polynomial p with this other polynomial. This is how I can actually get some counterpart of the group in the polynomial world. So I'll come to that, but let me say that I stated this bijective correspondence for all kissing reflection groups, not just the ones on the Beer's boundary of the ideal polygon reflection group. But if you just look at the Beer's slice boundary of the Beer's slice closure of the ideal polygon reflection groups, they correspond to antiholomorphic polynomials. And in fact, there is more. Let's ignore these things now. These are qualities on the contact graphs of the underlying circle packing, but I don't think I have time to get there. So there are special cases of this theorem. If your kissing reflection group is on the boundary of or in the closure of the Beer slice of the ideal polygon reflection groups, then the associated rational map is in fact a polynomial. And if there's a clean way of seeing this. This is not just an abstract bijection. In fact, this ties up with the theory of laminations too. So you see this limit set over here. This is obtained by pinching some curves on a punctured sphere. And the geodesic lamination that describes this limit set can be directly pushed forward by a homeomorphism to the lamination of this polynomial. And that's what gives you the homeomorphism between these two objects. Once you understand something for groups on the closure of Beer slice, you also want to understand what happens on the closure of the whole quasi-Fuchsian locus of of the ideal polygon reflection group. And it turns out, as expected, that groups that lie on the closure of quasi-Fuchsian groups precisely correspond to matings in the rational world. And how can we see that in, let's say, in one line? The point is, if you're on the closure of the quasi-Fuchsian locus, then such a group, if you're on the interior, that's easy. But if you're on the boundary, such a group is obtained by two measured laminations, essentially by pinching two measured laminations. And you can push forward the support, the corresponding geodesic laminations by essentially the homeomorphism between the Nielsen map and Z bar to the D to get a pair of polynomial laminations, and the corresponding polynomials realizing these laminations will give the mating of those two polynomials will give you the associated reflection or associated rational map. Let me say something more about this connection between anti-rational maps and reflection groups. So in fact, with Russell and Misha and Sergey, we showed that the dynamically natural homeomorphism between, or conjugacy between this limit set and this Julia set is not a quasi-symmetry. That's obviously seen from the cusp behavior here and the positive wedge, positive angle behavior there. Recently, Yusheng Luo showed us a rather elementary trick to show that there is really not even a dynamical quasi-symmetric homeomorphism taking this guy to that guy. But somewhat surprisingly, although they are not quasi-conformally equivalent, they have the same quasi-symmetric groups. They have isomorphic quasi-symmetric groups. One thing that I don't know, so we learned from In-Sung's talk that the Alfors regular conformal dimension of this guy, because this is a critically fixed map and it's a crochet map in the terminology. So this guy has Alfors regular conformal dimension 1. I do not know the Alfors regular conformal dimension of the Apollonian gasket, or more generally for the limit sets of kissing reflection groups. That would be interesting to know if, in general, whether the Alfors regular conformal dimension can distinguish the quasi-symmetric classes of these kinds of practices. All right. Now we are in a position to give a proof of the combination theorem. So let me try to give a proof using an example. So you have an antiholomorphic polynomial P, and you have a kissing reflection group on the closure of the Baire slice, and you want to mate the dynamics of the antipolynomial of the antiholomorphic polynomial with the Nielsen map of that kissing reflection group. For instance, if this is your antiholomorphic polynomial and this is your reflection group, you want to mate the action of P here with the action of the Nielsen map there on the filled Julia set, on the filled limit set. So the first thing is you replace, so let me write, this is P and this is gamma. Now instead of, so you forget gamma for the moment. Instead, replace gamma by this polynomial picture, the filled Julia set of this polynomial. And then you mate the P with that particular critically fixed anti-rational, anti-polynomial. And the assumption that there is no Moore obstruction can be used to prove that this P can indeed be conformally mated with this critically fixed anti-holomorphic polynomial. So that's where step 1, you use the connection between groups and rational maps. Step 2, you use Thurston realization theorem to conformally mate P and P gamma, where P gamma is the canonical critically fixed polynomial associated to gamma. But then the question remains, how do you perform, or how do you achieve what you really wanted? You didn't really want to mate P with another polynomial. That's standard. How can I mate P with the Nielsen map of this group? So the main thing is, the main key observation here is that the action of P, let's say this is gamma, or the Nielsen map of gamma, and this is the action of the corresponding polynomial P gamma. The action of N gamma over here and the action of P gamma on the Julia set, they are topologically, on the respective limit and Julia sets, they are topologically homeomorphic. All pre-periodic components eventually go to this guy and that guy. And the same thing happens here. All other two components map here and there. So the main difference lies in what's happening in these invariant components here and the invariant components there. So what's happening in the invariant component here? Well, this is a critically fixed map, so it's a z-bar square dynamics. And what's happening here? This is the Nielsen map of the ideal triangle reflection group. So you just really need to replace the z-bar square dynamics by the ideal triangle reflection dynamics, or in more general, the z-bar to the d dynamics by the Nielsen map of the ideal d plus one gone reflection dynamics. And this is something that requires a new surgery technique involving David homeomorphisms. And let me try to say why David homeomorphism is required here. So it's a standard fact known to almost everyone here that if I wanted to replace one expanding Blaschke product by another expanding Blaschke product, I could do that in the quasi-symmetric category by appealing to the Alfors-Building extension theorem. Unfortunately, in our case, the map z-bar square over here is an expanding map, whereas the Nielsen map here is a parabolic map. These are parabolic fixed points. So the conjugation between z-bar to the d and the Nielsen map is not quasi-symmetric. The standard recipe of simultaneous uniformization à la Beers does not work. What you need is a new extension theorem, some kind of an improvement of the Alfors-Building extension theorem for maps that are not quasi-symmetric. And this is something we proved jointly with Misha, Sergey, and Dimitrios. The theorem is stated in the paper in somewhat larger generality, but let me just state it for the context I need. So if you look at the map z-bar to the d and the Nielsen map of the ideal d plus one gone reflection group, any conjugation from this guy to that guy, it extends not as a quasi-conformal map, but as a David homeomorphism of the disk. So these are just generalizations of quasi-conformal maps with exponentially integrable dilatation. So the dilatation does blow up, but the region where the dilatation blows up, the area of that region shrinks exponentially. Once you have this extension theorem for circle homeomorphisms conjugating hyperbolic maps to parabolic maps, you can do a whole lot with it. So essentially, this puts several things into one unified context. Namely, you can turn a single hyperbolic rational map to a parabolic rational map just by replacing a hyperbolic Blaschke product or an expanding Blaschke product by a parabolic Blaschke product. You can go from a hyperbolic rational map to a Kleinian reflection group by replacing expanding Blaschke products by Nielsen maps of reflection groups. And you can also produce Schwarz reflection maps that are matings of antiholomorphic polynomials and reflection groups this way. So this gives you some kind of a strong hammer that allows you to go from hyperbolic setup to parabolic or mixed setup. And this is exactly what allows you to, at the end of the day, replace the z-bar square dynamics here by the Nielsen dynamics. So just to summarize the proof of the main combination theorem, you mate the polynomial with the partner polynomial P gamma. So you mate this guy with that guy, you get a rational map, and then in the rational map, you have a couple of critically fixed components and you replace them by the Nielsen map of ideal polygon groups. And the resulting Schwarz reflection map is, by construction, your mating. So here's an example of a cubic polynomial with it's a double basilica, so both critical points form two cycles. And the mating of this polynomial or anti-polynomial with the Nielsen map of this group is given by a very simple-minded Schwarz reflection map given by the exterior of an ellipse. We all know that the exterior of an ellipse is the conformal image of the exterior of the disk under the Joukowski's map. So the exterior is a Schwarz reflection map, and there are two disks inside here. So this is your piecewise Schwarz reflection map and the Schwarz dynamical system. So something so simple as an ellipse and two inscribed circles give rise to a conformal dynamical system that's a mating of this polynomial and this group. All right. Now let me slightly change gear and try to talk about some applications of the David homeomorphism theorem that we needed in order to prove the combination theorem. So now the rest is not going to is going to have nothing with combination theorem. Rather, we are going to reap benefits of the techniques that we developed so far. So this is again joint work with Misha, Sergey, and Dimitrios. Let P be an arbitrary geometrically finite polynomial with a connected Julia set. Using the David surgery technique, you can prove that the Julia set of P is conformally removable. This is something that we couldn't find in literature, although it's probably believed to be true. And also, if you take the limit set of a reflection group in the Beer-Slice closure of the ideal Degon reflection groups, such as, for instance, any of these guys, this guy or this more complicated thing over here, these limit sets are also conformally removable. And this is not a trivial thing to prove, because the standard way of proving conformal removability for these kind of Julia sets is that you prove that they are the boundary of some John domain. In these cases, they are not boundaries of any John domain. So for instance, if you take a parabolic polynomial, you know that the basin of infinity is not a John domain. There are outward cusps there. Similarly, if you take the limit set of a kissing reflection group that's on the Beer-Slice closure of the ideal polygon reflection group, they also have these cusps obtained by pinching. So they are not boundaries of John domains. You cannot use standard techniques to claim that they are conformally removable. However, you know, via the David surgery, as I mentioned over here, you can turn hyperbolic rational maps to parabolic rational maps and Kleinian reflection groups. And in this case, both these polynomial Julia sets and Kleinian limit sets can be realized as the image of a connected Julia set of a hyperbolic polynomial under a global David homeomorphism. Now the point is that for a hyperbolic polynomial with a connected Julia set, we know that the basin of infinity is a John domain. So its boundary is removable for this class of Sobolev function. It's W11 removable. And the main thing here is to prove that this property is almost preserved under the David homeomorphism. So since the Julia sets removable, is W11 removable, their images under the David homeomorphisms are conformally removable. So that gives that proves these removability statements. I'll skip these slides. Let me say a word on applications to conformal weldings. So the Julia set or the limit set of Schwarz reflection maps that we saw in the first slide in the deltoid case, that's not a quasi-circle. And the conjugation between the map Z bar squared and the Nielsen map of the reflection group of the ideal triangle reflection group is not a quasi-symmetry. So classical standard techniques basically tell you nothing about whether such a homeomorphism is a welding or not. However, dynamics tells you that these are welding maps. The Schwarz reflection map produces a Jordan curve, namely the limit set, which is the solution of the welding problem. So maybe let me just say what's a welding map. So if you take a Jordan curve in the plane, the external and the internal uniformizations, Riemann maps of the interior and the exterior, differ by some homeomorphism of the circle, and this is what is called a welding map corresponding to this Jordan curve gamma. And the question is, which homeomorphisms of the circle appear as welding homeomorphisms? Quasi-symmetric ones do. This is well known. On the opposite extremes, there are results of Bishop, which say something about existence of welding maps. It's also known that if you change a given homeomorphism just a bit slightly, then it becomes a welding map. But whether the given map is welding a homeomorphism or not is not easy to check in general. So the David homeomorphism technique that we developed, in fact, answers this question. So what is the precise statement here? So suppose you have two dynamical systems on the circle. Both are piecewise analytic C1 and expansive covering maps. Keep, let's say, the Nielsen map and Z bar to the D as examples, right? So both are piecewise analytic, expansive, and C1. They are of the same degree, and they satisfy some suitable Markov condition, which is a very soft condition. Essentially, these maps, they're expansive covering maps of the circle, so they obviously have Markov partitions on the circle, but you want these Markov partitions to extend to the whole disk, to a subset of the disk. And if these conditions are satisfied, which we have managed to check in many cases, then the maps are obviously topologically conjugate. They have the same degree and expansive, and the conjugacy is a welding map. Moreover, the associated Jordan curve that you get as a solution of the welding problem is conformally removable, so the welding solution is unique. And let me just show one interesting example of this sort. So what you're looking at is the Julia set of a cubic rational map. It's a quasi-Blaschke product, namely, there's a parabolic fixed point here, and this is the domain of attraction. And there's another parabolic attraction here, the parabolic fixed point here, and this is the basin of attraction of this brown guy. And this gives an example of a Julia set, a Jordan curve Julia set with infinitely many inward and outward cusps. So this particular Jordan curve is somewhat pathological in nature, in the sense that both the complementary components are non-John domains, and they're very far from John domains, because there are infinitely many inward and infinitely many outward cusps. However, this guy is conformally removable, and we believe that this is one of the first examples of conformally removable curves with infinitely many inward and outward cusps. All right, so let me try to end with, maybe in the last 2-3 minutes. Do I have 2 or 3 minutes?
No, you don't, I'm afraid, because we need to be at lunch at past.
Oh, okay, fine. I mean, I didn't figure. So it was a 1-hour talk, or a little less than an hour?
It was 50 plus questions.
Oh, 50 plus questions. Okay, fine. Then let me just end here. Okay. Okay, thank you.
Is there any quick question for, yeah?
In the earlier part of your talk, you had the picture of the Kleinian group limit set, which was these Apollonian circle packing, and then you said it was topologically same limit set was topologically the same as the Julia set of rational map, or maybe it was an anti. You probably phrase it like it was an anti-rational map, and that was the Julia set of Koch, Pilgrim, Booth, and others. I was just asking, is these Julia sets like that, can they actually be phrased as being a Julia set of like a combination theorem type rational map, or is it just it's only a combination theorem because it happens to be topologically conjugate to a limit set of a Kleinian group where there's a combination involved? So there's no concept of combination for just rational maps by themselves.
All right, so if I understood the question, so sorry, for some reason I can't share the slide right now. In any case, so if you look at the Apollonian gasket limit set, it is a mating of two groups on the boundary of the bare slice. Essentially, one can think of the Apollonian gasket this way. So if you look at, maybe. So this guy can be obtained from the circle by pinching two geodesic laminations. If you look at the ideal quadrilateral reflection group, the index 2 subgroup is a Fuchsian group with both the top and bottom Riemann surfaces homeomorphic to 4 times punctured spheres, and you pinch a curve upstairs and you pinch a curve downstairs, and this gives you the lamination model of this guy. So it's a quotient of the unit circle that pinches 2 geodesic laminations. So it's a mating of 2 geodesic laminations. Similarly, this picture is a mating of 2 polynomials. And in fact, this picture is a mating of this polynomial with itself, maybe a vertical copy of it. So if the fact that this is a combination of 2 groups automatically tells you that this is also a combination of 2 polynomials. And which polynomials this guy is a mating of can be explicitly understood from the measured laminations or the geodesic laminations that you need to pinch in order to get the limit set of this group. Is this what you asked?
The picture on the right is a mating, so yeah, that's useful to know that it was a mating in a manner similar to what you have for the Kleinian group example.
Yeah. Right. So this is, that's right. So this is the statement I tried to highlight here. So this dictionary between kissing reflection groups and critically fixed antirational maps gives a perfect parallel between matings in this world and matings in that world. So you can explicitly check which ones are mating. If you know one of them is a mating, you look at the lamination, the corresponding geodesic lamination in one world, and you can transfer those geodesic laminations to polynomial laminations on the other world. And then you get the two polynomials realizing the polynomial laminations, and the corresponding rational map is going to be a mating of those two polynomials. So they are consistently matings.
Any quick question from the people online?
So maybe just a very quick comment. So Sabya, you ask whether the conformal dimension of the Apollonian gasket is bigger than 1, and whether you can distinguish, these two things by the conformal dimension. And I'm almost 100% sure that the conformal dimension of the Apollonian packing is 1, and I think that more or less follows from a result of Carrasco, and there's like some sort of extension by Kinneberg. I have to check the precise statement, but I'm almost 100% sure that from it might even be written there, but from their work it follows that the conformal dimension of the Apollonian gasket is 1.
That's what Instant told me the other day. I asked him, that's what he said, that he was almost sure, so I didn't want to quote him. But yeah, is it also clear that, we know that the conformal dimension of all of these guys, the Julia sets of all of these guys is 1 because they are critically fixed, hence crochet maps. And they are all homeomorphic to the corresponding limit sets via some David homeomorphism. We don't know what whether the quasi-symmetric groups of this guy and that guy are different. We only know that in the case of gaskets, they have isomorphic quasi-symmetric groups, and you're saying that even conformal dimension cannot distinguish these things.
I'm almost 100% sure. I mean, as I said, I need to check the precise statement, but I mean, basically, it's if you have like locally finite points that disconnect, then the conformal dimension is 1, and I'm almost 100% sure that in this case you can easily verify it.
And so
is it clear that Apollonian gasket is L-force regular?
That's actually okay. So
I'm really sorry to interrupt. We are late for lunch, so I suggest that we thank our speaker again, and people online can continue their discussion.